I'm Ben from Los Alamos. We have kind of two talks. So the first one is I'm going to try and be quick and go through and just show how FleXCI uses Kokkos. So we have a very thin abstraction layer that's mainly designed to allow transparent interoperability between different backend runtimes that we use. And then Hyun is going to talk about a new radiation hydrodynamics application that's built on top of FleXCI. So if you don't know what FleXCI is, it's task-based. We have backend support for Legion, HPX, MPI. Functionality is not the same across all of those backends. We get sort of more fancy task-based parallelism with Legion and HPX than we do with MPI. And we originally developed the MPI backend as a risk mitigation strategy. So I guess the good news is if you use the MPI backend, there's very little overhead or really no overhead in the interface. And so you get some kind of a nice version of MPI. HPX and Legion add some more functionality. And then the other thing is we have provide topologies and data structures. So I'm just going to be talking about the runtime abstraction layer, but we have support for octrees and structured, unstructured meshes, and then some particle topologies so that you can do multi-physics application development. Yeah, so I'm going to talk about Kokkos. So this is just an anatomy of a task. A task is a normal C++ function. It can be templated. The thing that makes it a task is that you pass in these special accessor types. Just a simple example. The accessor arguments, we use privileges on the accessors so that we can create basically a task graph so that we know data dependencies between tasks, and then the runtime can reorder or move execution of those to different places. And that just allows us to keep maintain distributed memory coherence. So I guess in our case, tasks are fairly coarse-grained. This is something that where you would be doing quite a lot of work, and it can be distributed across different nodes. We have range-based iterators for the normal thing, and this is one of the main reasons why we have our Kokkos abstraction is to maintain our ranges interface. And then field access is just like C or Fortran, depending on whether you use our MD span or MD collex access. So going to the Kokkos version, this is the same code, but now I've put in this forall loop, and ultimately this is going to call parallel for in Kokkos, and I'm gonna dive down through it. FleXCI in the task, depending on where it runs, the runtime moves the data to the right place. So if it's running on device, or if you have an APU and it doesn't have to actually move memory, we have different strategies for doing that with a mapping utility. But it's transparent to the user. The forall, we have a new interface now that's going to be released in FleXCI 2.4 that uses this executor. We used to just have forall. This forall is actually a macro, and I'll dive down and show how it does that. But we use it to wrap the user's Lambda function for Kokkos, and we have some other extensions, so you can sort of extend this and define thread block sizes and information like that for optimization. And again, the main point of the abstraction layer is to make it so that this is all seamless between using Legion and Kokkos, or MPI, Kokkos, HPX, so forth. So the way that's implemented is we have that basic macro, and this is going to use the star operator to wrap the user's Lambda. This FleXCI macro forall just instantiates a forall T type that has that operator, and then that thing invokes a parallel for. So there's some layers here. Eventually, we get down though to where that's just calling Kokkos parallel for. So, and this works with different Kokkos policies. So a lot of the code that we use does MD ranges to collapse loops. And then for our parallel reduce, I guess the nice thing here is that we use type information to enforce some consistency between the reduction type and what the user's kernel is doing. So that's the end of that story, what we do. And we've been using this successfully for quite a while. The next thing, and I know this is getting beaten to death, why is partition spaces still experimental? I guess our feedback is that we like the current interface for using it, and I can beat on Davis and company to provide you guys with more feedback if that's what's holding that back. So I will do that. Port feature. Okay, so we have a bug, and Julian asked me to show this to you guys. So if we have this deep copy inside of our for loop here, we don't get any kind of concurrency. Where you see this is all serialized and green, blue, and red. If we just move that outside of that loop, then we actually get some concurrency. And so we figured that this is a bug, potentially. Okay. Yeah, so Julian's the right person to go with that. So that's the end of what I've got to say, and I will give it over to Hyun to talk about our application.
Okay, thank you, Ben. So then we'd like to show our one of the very first say application case called the HART, some new performance probable radiation hydro code. Why red hydro? The chosen is, of course, the honest sentence I should put it is that someone asked me to do. But red hydro is important because once you introduce the radiation, there are much more new physics, like span from that some astrophysical scenario and also some comet collision and some ICF type of the problem, which is topic of interest for the many national labs. And also hydrodynamics. I mean, you may see the people talks on the CFD, hydro, or MHD a lot. Numerical MHD is, so to say, relatively straightforward compared to the red hydro. There are many regions, like which equation we wanted to solve. Like you wanted to do the full transport, which can be 6D. If you want to choose the moment, if you want to choose the moment, which moment you want to choose it. Like what frame you wanted to do. So we need to something called the proper closure for the moment equations. And mathematical property also different. So that makes it numerical method is pretty complicated. And there are also some frequency dependencies at another dimension to the solution. So with this, introduce like extra layers of complication to implement and also run the simulations correctly, accurately, and efficiently. So this will be like perfect test bed for the FleXI framework and basic idea. FleXI also powered by co-design has been introduces this test-based infrastructure and is of course support like different backend, include Kokkos, and FleXI provide this and also all these like NRA entry unstructured meshes. We build something called the FleXI specialization, provide this, and on top of that, we can build this type of the, applications. So the meaning of the core design, we want a computer scientist, like computational scientists, and also application problem to build on top of each other. So let's solve it. So that's the governing system equation. I swear that's the last equation in my talk. So that's the hydro portion, some radiation energy. We specifically choose this form, something called a multi-group diffusion form. Then that's the usual approach. We apply something called a flux-limited diffusion approximation to treat the transport equation. And our governing system has the mixed hyperbolic parabolic system with we have a pretty stiff source term. I will explain what that means soon. And we apply some standard operator split schemes because radiation has the speed of light speed and also hydro is fluid. So they have a lot disparity between those two. Means if you just solve everything explicitly, you may encounter something called the time stepping issue. So we solve the hyperbolic subsystem, initially solved explicitly, parabolic subsystem that actually contain our radiation diffusion and source term, solved implicitly and update together. On top of that, we also support general equation of the state, means we can simulate it with different types of the materials. And we also tried to put some kind of different closures, better way to handle the multi-group are still investigating. So we wanted to show some example tests and why radiation hydro are interesting. So that's the one famous hydrodynamical instability test problem called the Alamos instability. Left-hand side is easy to think that this is just with the matter. And right-hand side, now we have some kind of strong radiation. As you can see, on the right-hand side, it has the much more this inspiral or say this barysis arm is building up. So that's the interesting phenomena. And we run on the really high resolution, perform with the 1024 square on the V100 GPU. Again, run on the exactly same thing. This is the hydro with the radiation. We see the clear distinction between those scenarios. Then we also doing some performance test, and the Chikoma is our test bed machine, or say institutional computing machine in Los Alamos that also has GPUs and a different thing. And then the FleXI support different backend. So we run the test case, something called the IMAX RK, radiation 1D test, run up to the 1024 GPUs, strong scaling, looks pretty okay. Some HPX has a kind of this problem. Being honest, we still don't know why. And then doing the exactly same thing, but now we are turning to the 3D. In that scenario, also we also doing strong scaling pretty well, up to about the 64 node. So our code is scales okay as a test case. And also we run the code on the GPU, so that's the single GPU performance. For the radiation hydro, we can reach up to 67 million cells update per second, which is pretty good compared with the Chikoma CPU node that is using the A100. And we also, for the comparison, how the 67 million cell update is good or bad. There's some another radiation hydro code that also have a GPU capability. So something called the Kokkos in their paper, they reach up to like a 39 million cell update using regular mesh and similar GPU ideas on it. So we are slightly outperform how Kokkos is doing it. And that's the how single GPU performance, relative time spent per actions, right-hand side the GPU, left-hand side the CPU, is pretty expected. So CPU really struggle to when they do the Jacobi solver or implicit solve, but it somewhat has the different relative time spending between the actions. And we are somewhat arguing we wanted to put this slide or not. Currently, we are focusing on to have a multi-GPU support, and as you can see, it is not great after 2 GPUs, which is pretty bad. That's the current our limitation. We are really working hard on it to have a good GPU support, so on it. So that's it. So FleXI is Kokkos abstraction layer, preserve range-based iterator logic, and provide the support for the Kokkos capability. And use that, we try to solve the radiation hydrodynamics problem, which is pretty challenging subject. And again, this FleXI specialization provide perfect work bed for the co-design. We pretty feel that we successfully demonstrated this basic rate hydro test, and the ultimate goal is we wanted to add like more physics module to have our target inertial confinement fusion simulations. And our code is open sourced, so if you're interested in it, please check it, clone it, run it. If any issue, please put the pull request. I think that's it. Thank you.
All right, any questions on either parts of the presentation?
Yeah. We did both. So we increased like the typical strong versus weak scaling case, and both cases our scaling is really bad.
Which was that?
Which one?
Was that strong or weak?
Both. So that's the strong and that's the weak. Yeah.
The mic.
Not really a question, it's a comment. It was pretty bold, the forall macro. Is it something Davis approved?
Did Davis approve it?
Yeah,
He
approved.
extended it. I can't even take credit for it. Like this guy named Nick Moss did the first thing. And somehow, I mean, I was very surprised that it still exists, but it's a useful way to just wrap the.
No, it's just that the risk of collision is not.
We have a little. Well, I don't know. I think originally it was to try to make it sort of a simplified interface for.
No, I think David meant the name, right? And
Yeah, the
forall
name.
is not a very uncommon name, right? So it's a bold choice format, right?
Yeah. I don't know. We haven't any trouble with that. I mean, now the real reason that it still exists, though, is that it allows us to sort of have interoperation between the lines and make sure that we are in the right place. And all all of that code diagram validates it, so it's all work on this issue. We still already.
So there are in the Los Alamos, there are another solver project called FleXsolve. Now you can see where their name FleXsolve came from. So we built a solver library on top of the FleXCI. We are using it. Yeah. Yeah, that was open source too.